We'll take a look at our homework from last night, page 492, questions 1 and 2. We're going to start off, question number 1. It says a 2,000 kilogram car traveling at 20 meters per second at 90 degrees. We saw yesterday that angle convention that they tend to use in this textbook. We don't need to worry about it too much because we're not going to see that on our diploma exam, but we've got to be able to do the questions that they put in the textbook. 90 degrees means it's going this way. We'll call that object number 1. It has a mass of 2,000 kilograms, and it has a velocity of 20 meters per second at 90 degrees. There's a 2,500 kilogram pickup that's traveling at 180 degrees. 180 degrees is this way. We'll call that object number 2. Its mass is 2,500 kilograms, and its velocity is 14 meters per second. They stick together upon impact, and we want to find the velocity of the center of mass of the car-truck combination immediately after the collision. Where do you think it's going to go? I'm not asking you to predict an angle for me right now, but I'm going to ask you to predict a general vicinity that it's going to go. Is it going to go down and to the left? Is it going to go up and to the right? Is it going to go up and to the left? Where's it going to go, Carrie? Yeah, we know it's going to go up and left up here somewhere, right? Somewhere up there. We know that because if there's momentum to the left before the collision, then there has to be momentum to the left after the collision. If there's momentum upwards before, then there has to be momentum upwards after the collision. So we know it's going to go somewhere up there. Now, how exactly do we figure out where it's going and at what velocity that it's going at? Remember we said over the last couple of days that when we see a problem like this, it's really 2 problems. Sorry, it's really 3 problems. We've got to turn this problem that's got a vertical axis and a horizontal axis into a vertical problem and a horizontal problem, and then recombine them as our 3rd problem. So let's do that now. Let's do the horizontal, our x components here. We know that we have 2 objects. So we're going to say m1 v1i plus m2 v2i. And afterwards, they stick together, so we're going to say that they have just one momentum, mvf. What's the mass of object number 1? 2,000 kilograms. What's the velocity of object number 1? Sam? No. What's the velocity of object number 1? Grant, what's the velocity of object number 1? 0. 0. How come it's 0, Grant? It's not moving to the left or right. Okay, we're moving on the y-axis here, and we're analyzing the x-axis. Remember we said when analyzing the x-axis, ignore anything on the y-axis. So we're not paying attention to that 20 meters per second or that 2,000 kilograms right now. M2 is 2,500 kilograms. V2i? V2i? Down, what's V2i? Almost. Good. Negative 14 meters per second because it's going to the left. Good. Now, the combined mass, we have to pay attention to mass number 1 now. The combined mass, 4,500 kilograms. We got to pay attention to mass number 1 now because after the collision, it's got an x component to it. Okay, not completely x, it's going up and to the left, but part of it is going to the left. So we have to pay attention to that mass now. 4,500 kilograms times VF. Let's solve for VF there. We get negative 7.77778 meters per second. It's not a final answer, right? That's the x component of our final answer. Now we need to do the y component, the second of the 3 problems. For the y component, once again, we're going to say pi equals pf. We have 2 objects before the collision. We have 1 object after the collision. Scroll down, scroll up here so we can see this diagram again. M1, 2,000 kilograms. Mitchell, what's V1I? 20 meters per second. Okay, we're not ignoring that this time because we're looking at the x component, sorry, the y component. M2, 2,500 kilograms. What's V2I? Dickie, what's V2I? 0, right. We're looking at the y component and we're ignoring anything on the x component. So we're going to drop this. The combined mass is still 4,500 kilograms times VF. We solve for VF here. Thank you. We get 8.888 meters per second. Good. 2 of the 3 parts of this problem done. Now we've got to recombine them. So let's say the X component was 7.7778. It's not necessary to put a negative in there because the arrow is showing us direction, right? Actually, let's move that a little bit so we got space to draw the other one. 7.7778, and then the Y component is positive 8.8889. We predicted that the final velocity would be up and to the left. Sure enough, it turns out to be up and to the left. We were right in our prediction. Let's solve for that V using the Pythagorean theorem. And let's solve for the angle. Lots of people ask, where do I draw the angle? Which spot on the diagram do I draw the angle? The angle is always drawn at the start. Okay, this is where the vector diagram starts, so let's draw the angle at the start. We're going to find it by saying it's the inverse tan function of opposite 8.8889 over hypotenuse. I think when we get solve for V, we're going to end up with 11.8 meters per second. And when we solve for theta, we're going to end up at, calculate the angle there, we get 49 degrees. Now, with the way that they express it here, the frame of reference that they use here, 49 degrees there, well, this would be 180. So 180 take away 49 gives me 131. And they're always measuring it from the x-axis there. Why do they use that frame of reference? They don't always. You see, question number 2, they use west and south. Question number 1, they use this crazy frame of reference that we're not used to. How come? Well, because sometimes we don't know which way is north, right? Sometimes we've got a collision taking place between 2 objects. We're in a darkened room or a room with no windows, and we don't know which way is north, south, east, and west. So we have to have some frame of reference. We define 0 degrees as to our right. However we're standing. If I'm standing this way, 0 degrees. If I'm standing this way, 0 degrees. And then we always measure it from our right, right? If we don't know which way is north, south, east, or west, then we can measure it that way. Does that make sense? That's kind of why they're using that in some of these questions, but in other questions, they're using north, south, east, and west because they're assuming that they know what direction north is. Nick just asked a real good question, or pointed out something that was really interesting. He says, I just calculated the momentum on the x-axis, and then I calculated the momentum on the y-axis before the collision, right? And then did the Pythagorean theorem. What did you technically find, Nick, when you did that? If you said 2,500 times negative 14 gives me the total x momentum, and then 2,000 times 20 gives me the total y momentum, and then you combine them, what did you technically find? You found the total initial momentum, right? You calculated this, and then you put the 2 of them together in a triangle, and then you would have divided by mass to get the total mass to get the velocity. You found the total initial momentum. What did we do? We found the final velocity. What's the difference? Well, besides momentum and velocity, that's not a big deal, because to get velocity, you just have to divide by mass. You did initial, I did final. Why did we end up with the same answer? Because the initial momentum is equal to the final momentum. Does that make sense? So that's right. That's fine. Now, that tends to work quite well, actually, with 90-degree collisions. Now, I'm doing it a little bit more, probably a way that takes a little bit longer and shows a little bit more work, because as we do problems that aren't involving 90-degree collisions a little bit later on, this is really useful. So I'm trying to get you in the habit of that. But Listen, I'm never going to say, no, don't do that for 90-degree collisions. Just be aware of how to do this because this is going to be a little bit more important later on. Okay, bottom line is it works because initial momentum equals final momentum. So I calculated final, you calculated initial, doesn't matter, it's the same thing. Okay, let's take a look at question number 2. It says a 100-kilogram hockey center is moving at 1.5 meters per second to the west in front of the net. Let's draw it out here. We're going to call him object number 1. His mass is 100 kilograms, and he's moving at 1.50 meters per second. We got object number 2 that's going to the south. His mass is 108 kilograms, and his velocity is 4.20 meters per second. They move off together after the collision. They embrace after the collision, and they head off as one. 2 hockey players hugging each other after this collision, going off somewhere southwest, somewhere. Where exactly? We don't know exactly. We'll figure that out in a second. But we know the general vicinity is going to be south and west. We want to know the velocity of the center of mass of these 2 guys. Well, we know what to do, right? We know that this is an X problem and a Y problem. So let's do that. We're going to say, once again, 2 objects, M1V1I plus M2V2I equals MVF. 2 objects combine to form 1 object after the collision. 100 kilograms times, Dylan, what's V1I? What's V1I X component? Almost. Almost. Caitlin, what's he missing? Negative 1.5 because it's to the left. AM2 is 108 kilograms. What's V2I? Hannah, what's V2I for the X component? Good. 0, because we're on the X-axis. We're ignoring anything on the Y-axis, right? The combined mass is 208 kilograms times VF. We'll solve for VF here. 0.72. Is there more decimal places? Anybody else have? Okay, 0.72115. Okay, let's go to 4 or 5 decimal places until it's a final answer, right? Usually it's not a big deal, but every once in a while, maybe 2 times out of 10, it makes a rounding issue for your final answer. So instead of getting 6.39, you get 6.38 or whatever. And if that's a multiple choice question, it's probably not going to be a big deal because you're going to notice that, right? But if it's a numeric response and you put 6.38 instead of 6.39, then you get it marked wrong. So we want to leave those in-term answers as unrounded until we get to a final answer. All right, good. X component 0.72115. Let's do the Y component now. Once again, PI equals PF. M1V1I plus M2V2I. Same deal as before. M1 is 100 kilograms. What's V1I? What's V1I, Ali? For the Y component. Good. Okay, we're on the Y component. We're ignoring anything X. And that's what V1I was. V2I. And well, M2 is 108 kilograms. V2I, who haven't I got here? Laura? Yeah. Almost. Good. Negative 4.20 kilograms. And the combined mass is 208 again. Caitlin, do you have what VF is there? Thank you. Now we got to recombine them, right? We say negative 0.72 and we have negative 2.1808. There's my resultant vector that we want to find, and there's theta. So we solve for V using the Pythagorean theorem, and we get 2.30 meters per second. And we solve for theta using the inverse tan function, 2.18 over 0.72. And we end up getting 71.7 degrees. And they do express this one as a south of west because that was the frame of reference that they gave us in the question. Right? Carrie? Point. Carrie's point, Carrie just made a point here. She said, wouldn't it make sense to write VFX and VFY for this? Yeah, you know what? Absolutely. If that's helpful to you, then absolutely do that. I used to do that, Carrie, to be honest. In fact, I used to put an X all the way through it. I would say M1 V1I X plus M2 V2I X and so on, and do similar down here for Y component. I just found it got so cumbersome with the subscripts that I started dropping them and just making sure that I had them labeled clearly up here, okay, so that I could distinguish there. But by all means, okay, if it's helpful to you to label that VFX instead of just VF, VFY instead of just VF, then absolutely. I think that can be a good idea to do. Yeah, absolutely. You have to have it shown somehow that it's X component and Y component. I had it shown, but I mean, no question, that's better. It's better to show it that way. It's just striking that balance between doing that and having a cumbersome amount of subscripts, that's all. Right? All right, well, let's have a look at this one. This is more of an explosion than a collision, but that's okay. Still use conservation of momentum. A 0.6 kilogram fireworks bundle is at rest just before it explodes into 3 fragments. A 0.2 kilogram fragment flies to the west, a 0.18 flies to the south, and we want to find the third one after the explosion. No mass is lost, and the motion of the fragments lies in a plane. They're telling us here, since no mass is lost, then we don't have any momentum lost due to some object that we don't know about. And the motion of the fragments lies in a plane. In other words, it's like this, making it a 2-dimensional problem instead of like this and like this, making it a 3-dimensional problem and having to deal with it as an X, Y, and Z problem, right? We're not going to do anything like that, by the way. Let's draw this out. Here's my explosion point right there where the X is. After the explosion, we have a piece going to the west. We'll call that piece number 1. I guess they call it ABC. I'm going to continue calling them 1, 2, 3. I don't like saying like VA initial, VAI. Okay, I don't know. Too many letters confuses me. I'd rather say V1I. But if you want to call it object A, that's fine. It doesn't really matter. Object number 1, 0.20 kilograms, and it's got a velocity of 14.6 meters per second. Object number 2 goes to the south. It's got a mass of 0.18 kilograms, and it's got a velocity of 19.2 meters per second. Where do you think object number 3 is going to go? Make your prediction now. Commit to something. Where do we think object number 3 is going to go? Nick? Like down here? How many people think that Nick is right? Down between object 1 and 2. Okay? How many people think he's wrong? Okay, more people agree with you, Nick, than disagree with you. Problem is they're wrong too. It's not going to go down into the left. Okay. Listen, think about this. What was the momentum before this explosion took place? What was the total momentum before this explosion took place? 0, right? 0. What's the momentum after it takes place? 0. Well, if there's 0 momentum afterwards, and we have momentum to the left, then we have to have momentum to the right to counter that. And we have to have momentum up to counter the momentum that's down. So we don't have it going down and to the left. We've got it going up and to the right. Does that make sense? The total momentum has to remain the same. If we had it down and to the left, that would make it a whole bunch of left and a whole bunch of down momentum, whereas we should have zero. Down and left. What's the mass of the third piece? Do we know that? What is it? How'd you get that? Good. Total mass is 0.6. It's only 3 pieces, so we subtract 0.2 and 0.18 from 0.6. We don't know the speed, that's what we're trying to find. All right. Okay, same deal. It's an X problem, and it's a Y problem, and then it's a combined problem. It's an X and a Y because clearly we've got stuff going on 2 different axes, an X and a Y axis. I like these ones, though, better than the T-bone collisions, because the initial momentum of these ones is 0 if it's not moving. Problem is we've got 3 objects afterwards, so an extra term there. I think this is the first time we've seen a problem where we have 3 objects. Well, actually, we had one on our quiz, right? We had 3 objects, except it was a one-dimensional problem. V1F is negative 14.6 because it's to the left. What's M2? Elizabeth, what's M2? Sorry, M2. I'm not going to ask you what M2 is. 0.18 kilograms. That's easy. I'm going to ask you what V2 is. V2F for the X component. Yeah. No, that's object number 1. This is object number 2 right here. And from where you're sitting, it's probably kind of hard to make out that number. That would be the, Austin? Yeah, that would be the Y component, right? And when we're analyzing the X component, we're going to ignore the Y component, right? So Austin, you're right, it's going to be 0. Cross that off. This should be M3. M3 is 0.22. And we solve for V3F there. At 13.272727 meters per second. Do the same thing for the Y component. M1 is 0.2 kilograms. Elizabeth, what is V1 for the Y component? Object number 1. Yeah. Object number 1 for the Y component. Remember, when we're analyzing the Y component, we ignore anything X, right? So it's 0. Good. Analyzing X, ignore Y. Analyzing Y, ignore X. 0 times 0.2 kilograms is 0. Mass number 2, 0.18 kilograms. V2F, negative 19.2. Negative because it's going to the south there. M3, 0.22. V3F, that's what we're looking for here. You get 15.70909 meters per second. And hey, listen, we know what to do at this point. It's exactly the same as the example problem I gave you yesterday and the 2 practice problems we had for homework last night. At this point, we just recombine them. We got 13.272727. We have 15.70909. Could solve for V, solve for theta. V is the square root of 15 squared plus 13 squared, and theta is the inverse tan of opposite over adjacent. Solve for V, Sam, we get 20.57. We're going to round that to 21 meters per second. Thank you. Should be 3 digits, yep. Or 2 digits, I mean. And on this side of the room, theta was, who's got it? Okay, you got it? 49.8. Yes. We're going to round that to 50 degrees. And our frame of reference was north, south, east, west. So this would be 50 degrees north of east. Let's have a peek at these two questions at your desks, please. Okay, focusing on number one here, it says a 0.058 kilogram firecracker that's at rest explodes into 3 fragments. One goes to the north, one goes to the east. Where's the third fragment go? Here's our explosion point right here. We got one object number one that's going to the north, 0.018 kilograms with a velocity of 2.40 meters per second. We got another piece going to the east. We're calling that object number two. It has a mass of 0.021 kilograms, and it has a velocity of 1.60 meters per second. Now, somebody was asking me, as I was walking around and watching what you guys were doing, somebody was asking me, how do we find the third piece? Like, how do we find where the third piece goes? Okay. Sometimes I make assumptions that you guys know something that you don't know, and that's sometimes not a good thing. This is going to go down and to the left. But how do we know the third piece is going to go down and to the left? Well, the initial momentum of this bomb, or this firecracker, I should say, is 0. The final momentum is 0 on both the x and the y axes. So if the initial momentum is 0, and the final momentum is 0, and this guy has, I don't know, let's say 10 units of momentum to the east, well, then there has to be 10 units of momentum to the west to counter that. And if this one has, let's say, 10 units of momentum to the north, then there also has to be 10 units of momentum to the south to counter that. Right? 10 plus negative 10 gives me 0, and the total momentum is 0. So we have to counter every momentum that we have there. If we have one to the right, we have to have one to the left. If we have one to the north, we have to have one to the south. So we know this is going to the left and down to counter the right and up. All right, let's break it into our x's and our y's here. The initial momentum, again, is 0. Now, this firecracker was moving when it exploded. We wouldn't say its momentum was 0, right? We'd say it's mvi. Now, there's 3 objects. So we got 3 terms. If we're lucky, and every once in a while this happens, something explodes and it breaks apart into 3 equal-sized pieces. Okay, why do I say if we were lucky it would do that? If it broke apart into 3 identical pieces, it would simplify things for me because I would be able to cancel the mass, right? If all the masses were the same, I could cancel them, which makes the math in my calculator a little bit easier, but it's not a big deal. Object number 1 is going only on the y-axis, so we ignore it. Object number 2, 1.60 to the right. Object number 3 has a mass of, what is that mass? 0.058 minus 0.018 minus 0.021? 0.019 kilograms times V3F. Who's got a value for V3F there? Or this goes over by subtracting, right? So V3F becomes 36923, thank you. Negative, right, because it comes over by subtracting, divided by 0.019 gives me negative 0.36. That's important, right? The negative is important. You're going to get the same magnitude, the same hypotenuse, whether you make it negative or not, but you're not going to get the right direction. Zero initial momentum. Final momentum is 0.018 times 2.4 plus 0, because object number 2 is only on the x-axis. Make a mistake here. What is it? 1.7684. The third mass, 0.019 times V3F. Sam, do you have V3F for the Y component? Two seven three six eight. Thank you. Agree with that? Now we combine them, right? So we're going to say 1.76, 2.27, and then the hypotenuse, and then the angle. Solve for the hypotenuse using the Pythagorean theorem, 2.9 meters per second. And we find theta by the inverse tan function of opposite over adjacent. Which gives me 52 degrees south of west. Good. I got one more example for you, then you can stop listening to me for the day, okay? Page 490. A 19.6 kilogram curling stone moves 1.2 meters per second to the north, strikes another identical stationary curling stone off center. Off center is important because when it strikes it off center, it means that one's going to go one way, one's going to go another way, right? If you got a curling rock and you strike it bang on in the middle, then you know that they're going to keep going in the same direction that they started. We have one of them going off at 1.17 at 12 degrees east of north. This is similar to that question number 2, right? We have a direction that's kind of wacky, like east of north. What's the velocity of stone B after the collision? Ignore frictional and rotational effects. We always ignore frictional and rotational effects, right? Whether they tell us to or not. Bottom line is that we have to, because if, especially something like curling, right? Rotation is actually pretty important sometimes in curling because that's what causes the rock to curl. Between friction and rotation, it causes the rock to, when you're sending it down, can do this, right? Because of friction and rotation of the rock. We're ignoring all that stuff. Let's draw a picture here. It's a collision. We know it's conservation of momentum. We know it's going to be in 2 dimensions. We know it's going to be in 2 dimensions, even though we don't have an X and a Y like a T-bone collision. We clearly have X and Y whenever we have a funny angle like this. All right. Curling rock 1, 19.6 kilograms, a velocity of 12 meters per second to the north. Strikes curling rock 2, which is also 19.6 kilograms at 0 meters per second. Curling rock 1 goes off with a velocity east of north. So number 1 goes up this way, still 19.6 kilograms. Goes off at 12 degrees east of north with a speed of 1.17 meters per second. Where do you think rock number 2 is going to go? I mean, seriously, like, you don't even have to know the physics of this, but just intuition from experience can tell us this. Okay, if you glance, if object number 1 is glancing number 2, and object number 1 goes off to the right, then object number 2 is going to go to the left, right? It's going to go up here somewhere. Where exactly? We don't know. With what speed? We don't know. That's what we want to find. Now, this is the first time you're going to hear these words in Physics 30. But I guarantee if you had me in Physics 20, it's not the first time you've heard these words. Some of you, those of you who had me in Physics 20, should look at this question and right away think of 5 words. I don't like funny angles. Every time we saw an angle that was like 12 degrees north of east, or east of north, I guess it is, or whatever, some funny angle that wasn't 90 degrees, we said in our minds, I don't like funny angles. And we're going to do that again this year. Every time we see an angle like that, we're going to say, I don't like funny angles. What do, Carrie, when we see angles that we don't like? We get rid of them. We get rid of them. So let's draw this off to the side. 12 degrees, 1.17 meters per second, This is x, this is y. Let's get the x component of that and the y component of that. Don't worry about how to solve this question yet, the final answer. Let's just deal with one thing at a time, okay? We don't like funny angles. Let's get rid of the funny angle. We're going to say sine 12 degrees is equal to x over 1.17, because x is the opposite side. We have the hypotenuse, right? Sine 12 is equal to opposite over hypotenuse. For that, we get 0.2433 meters per second. That's the x component. Now the y component, cosine 12 degrees is equal to y over 1.17, right? Cosine 12 is equal to adjacent over hypotenuse. For that, we get 1.1444 meters per second. I'm telling you this, every time you see a funny angle, and by a funny angle, I mean something that's not 90 degrees. Every time you see a funny angle, you need to do this. I don't care whether it's in the context of conservation of momentum or in the next unit we do something called Coulomb's law, or if it's a physics 20 problem where the captain of a ship is aiming, towards across the harbor or whatever, right? Those navigation problems that we saw in physics 20. I don't care. I don't care what the context of the problem is. Every time you see an angle that's not 90 degrees, what I call a funny angle, you got to go off to the side and you got to resolve it into x and y components all the time. All right. Now, what we could do, we don't have to redraw this if we don't want, but I will this time at least. I'm going to redraw it and pretend that that 1.17 is gone now. I got a 0.2433 to the right and a 1.1444 upwards. Now I don't have a funny angle anymore. There's one right here for the red one, but I don't know what it is, so it doesn't really matter. You don't have to redraw that, but that redrawing it might, and you see in a second here, might make it a little bit easier to deal with when we do PI equals PF. All right, so PI equals PF. M1V1I plus M2V2I equals M1V1F plus M2V2F. Oh, good news. Good news. What's the good news? What's the good news besides there's only 10 minutes left in class and you're getting your last example problem and you don't have to listen to me anymore after this? What's the good news? Done? Masses are all the same. Now, usually masses don't cancel, but this time they do. Okay, that's good news. V1I is 0 because we're dealing with the x component here. V2I is, oh, good news. That's 0 too because it's at rest. So the total initial momentum on the x-axis is 0. V1F, this is where I'm testing you. What's V1F for the x component? Olivia, you got that one? Sorry? Point two, did you say? Or did you say 1.2? No, not 1.2. What is it? No. Listen, this is done. No, sorry, wait a sec here. We got rid of the 1.17. It's done, right? We're never going to see that again. We're never going to use that again. We resolved that. We got rid of a funny angle, 12 degrees south of east, 1.17 meters per second, and we changed it into 0.2433 to the right and 1.144 upwards. So we're going to replace V1F with 0.2433. Right? The x component of the velocity that we resolved, plus V3F. Well, this is really easy to solve for. V3F ends up being equal to negative 0.2433 meters per second. Now let's do the y components. PI equals PF. M1 V1I plus M2 V2I equals M1 V1F plus M2 V2F. Masses cancel. V1I, 12 meters per second. Sorry, 1.2 meters per second, isn't it? Is it 1.2 or 12? Yeah, 1.2. 1.2 meters per second, because look, the first object is moving at 1.2 to the north before the collision. We're dealing with the y component. We ignored that when we were doing x, but now we're doing y. So we got to pay attention to that. Plus, oh, this is 0, because it's at rest. V1F. I said before that the V1F was the real test for the x component. No, now it's the real test, right? Because I gave you V1F for the x component. Now you're going to tell me what V1F is for the y component. Good, Jacob. V1F is 1.1444. Look what I've done here, guys. I've replaced the 1.17 with an x, and I've replaced the 1.17 with a y. I've changed the 1.17 at the funny angle into a 0.24 and a 1.14. And those are the numbers that I use now. Add that to V2F. Solve for V2F. 1.2 minus 1.144. And I resolve it, right, just by saying 0.2433, 0.0555. You can do this, right? V is the square root of 0.055 squared, 0.24 squared. And theta is the inverse tan of 0.05 over 0.24. How is this question different than what we've done before? Had a funny angle, right? What do you say? What do you say when you see a funny angle? I don't like funny angles. 5 words. So get rid of it then. If you don't like it, change it into an easy X and an easy Y like we did there. Your homework tonight, beyond the 2 questions you were just working on a few minutes ago, tackle question number 2 now. You're better equipped to handle that. In addition to that, I want you to do the 2 questions on page 491, please.